the American Committee on International Relations and Statistics Without Borders. And as usual, I want to thank Donna from ASA for all her work coordinating and also for being one of the people who began the webinar with us. And of course, Alex for also being kind of the initiator of this effort. And of course, to Natalie for kindly agreeing to host. And thank you all for coming. So I'm going to introduce Natalie, and I'm gonna make some announcements at the end. So please stay tuned at the end. We're gonna talk about future, the next webinar and some other really exciting announcements. Okay, that being said, so let me introduce Natalie. We're very lucky to have Natalie with us here today. Natalie Shlomo is a professor of social statistics at the University of Manchester and publishes widely in topics under survey statistics and methodology. She has over 70 publications and refereed book chapters and a track record of generated external funding for her research. She's an elected member of the International Statistical Institute, a fellow of the Royal Statistical Society, a fellow of the Academy of Social Sciences, and president of the International Association of Survey Statisticians. She also serves on national and international methodology advisory boards and editorial boards. So thank you again, Natalie, for agreeing to talk. Also, one logistical issue is that please put questions in the Q&A rather than in the chat. Okay, thank you. So the floor is yours, Natalie.
Okay, let me just get my slides up and you can hear me. I unmuted myself. Let's get this full screen. There we go. Okay, well, thank you so much for inviting me to give the webinar. I'm very happy to be here today to talk about record linkage. And so I will have, about 55 slides or so. I'll try and go through them slowly. And I will stop periodically if you have questions. I hope somebody there can monitor the questions because now I'm on full screen on my presentation and I don't really see the Zoom link anymore. So let's have a go. So as Carolina said, I'm currently based at the University of Manchester, but I'm originally from Minneapolis, Minnesota. So somebody has joined us from that city as well. So big shout out there. And so I'm going to cover the following topics in this lecture. I'll start with an introduction and what is record linkage. Of course, record linkage, about 99% of the work in record linkage is the pre-processing and defining string comparators and how we set up the data, set up the possible pairs to compare, the comparison space. And so we'll talk a little bit about all of that pre-processing stages. Then I'm going to get into probabilistic record linkage, and I'm going to follow pretty much the theory in that original seminal paper by Fellegy and Center. So we'll get a little bit of statistics in this talk. And I will follow it with discussing the EM algorithm and how we can adjust these scores to determine the probabilities of a correct match. And I've finished this area under, with the thresholds and evaluation and how we assess and evaluate the outcome of the record linkage. And then I'm going to have a few slides a little bit on new extensions, because of course, since 1969, when this original Fellegy Center paper came out, a lot has happened. And actually, it went a bit dead in the 80s, 90s, but of course, nowadays, the statisticians were really, it kind of went to the computer science field, and then statisticians came in to start working on it. And it certainly became very prominent with the work going on at the Census Bureau at the time for their coverage surveys and in the years of 2000 and 2010, and subsequently now all these new applications and with Bayesian applications. So I'll give a little bit of mention on these newer extensions. And then finally, I do want to say a couple words about how we analyze linked data. So a few slides on that. So without further ado, I will make a start. So I'm going to start with an introduction to record linkage. Now, record linkage is the notion that we have two data sets, two or three of many data sets, and that the same individual, the same person or entity or whatever we're trying to link is on these two or three different data sets. Now, this is opposed to things like statistical matching, where we're trying to bring entities together, but they might not necessarily be the same person. So here we have two different sources of data, three sources of data, and we assume that the same person belongs, in these data sets, and that we want to bring them together. Now, the idea is that if these two records or the pairs, if they agree on all matching variables, that wouldn't have happened by chance, and that the level of assurance that this link is correct, that pair actually belongs to the same person, will be high, right? So I want to try and quantify how high. Now, if all of these matching variables disagree, then we can assume that this pair will not be linked together, right? And it doesn't belong to the same person, and we can make a decision about that. But the problem is the intermediate situation. So this is where some matching variables might agree and some matching variables might disagree. And therefore, we need to set up a prediction problem. We need to set up a prediction to decide whether this pair that we're comparing is a true match or a non-match. And ultimately, we're going to probably have to include some sort of manual or clerical review to determine the match status. And this is all about, this theorem that was developed in Felige-Center and how we get that optimal set of matching pairs for clerical intervention. So record linkage, the idea of probabilistic record linkage is to allow for errors in these data sources, in these matching variables. So when we have no sort of unique high quality identifier like an ID number, national statistics, social security number, any sort of ID number, if they're not available, we're going to have to try and match on less stable information. So record linkage typically has three stages to it. And as I said, the pre-linkage, that's all the data cleaning, the parsing, splitting the fields up, standardizing these matching variables is a huge amount of work. And this is actually about 99% of the whole process in record linkage. And I do want to give a shout out to a recent article that I was reading, looking, as I was developing these slides or updating these slides, because I've given this course many, many years already. I did see a paper by Rebecca Stutz who talks about the data cleaning pipeline. And by the way, the last slide has all of these references that I'll be citing, so you'll have the citations as well. So the pre-linkage is about 99% of the work. And then what we need to do is to produce a comparison space. So bringing all possible pairs, say if we've got two data sets, then all possible pairs from these two data sets, we want to bring them together, compare them on their matching variables, and be able to determine statistically whether this is a correct match, whether they belong actually to the same person. And then finally, the last step is this post-linkage. This is all about the evaluation and the thresholds and how do we determine error rates and how do we carry out our analysis, checking the residuals, who linked, who didn't link. So that's the post-linkage process. So as I mentioned, if we don't have high quality ID numbers, we have to link on matching variables that are sort of less stable. But the properties needed to determine whether this would be a good matching variables is that the matching variable has to be unique and, of course, available. They have to be known and accurate, right? We want to have very minimal errors possible on these matching variables, and they have to be stable over time. So would I use, say, first name as a matching variable versus last name. We know last names can change over time, or addresses can change over time. So it might depend on the timeliness of these two data sets and whether we can get them, based on the same time. Certainly census coverage surveys would be stable over time. And there's a lot of linkage done, obviously, in last names and first names. So we'll get into some case studies later. But just as an introduction, these are the 3 stages of linkage, and we need to determine what our matching variables will be. So, of course, I don't want to talk about record linkage without talking about what we all do in all of our statistical packages, and that's deterministic exact matching. So for exact matching, of course, the records in the 2 data sets have to agree exactly on the matching variables, and bit by bit, each character of the matching variables, in order to conclude that they correspond to the same person. And typically we would do this if we did have a high quality ID number and they're available. And you might think about linkages as being multiple iterations. First of all, doing an exact deterministic link and then moving to the probabilistic link. So there's all sorts of scenarios there. But any deterministic link, of course, each matching variable and each character of matching variable has to match exactly in order to determine this the pair to be a link. And it's notable that in this case, all the matching variables have the same weight associated to them. So that matching on gender carries the same weight as matching on your last name, right? So this is what's going to happen in our probabilistic linkage. We're going to be able to put on different weights on these matching variables depending on how well they can uniquely identify an individual. So that's exact matching, and I'm sure we've all done this in our work, everyday work, and we have packages that do this, deterministic methods in statistics. Now, there is a lot of work, it's certainly in the computer science literature, which is called fuzzy matching. So in this case, they do try and do a deterministic exact match, but in this case, they try and allow for some errors in the data. For example, Google, does wildcard substitutes for characters. So they might do star A, star A, star A, and then that can represent anything like banana, pajama, etc. So that's a type of fuzzy matching. Anytime we can do an exact match, but allow for a little bit of introduction of errors. Other ways is to, instead of matching bit by bit on each bit, a character of a last name, for example, we can think of transforming this data using a phonetic code or only using the first 2 or 3 letters of the name. All of this allows for potential errors to creep into that deterministic matching. So I won't say much further here on the fuzzy matching and deterministic matching, but I did want to mention it because this is also going to come into play in the probabilistic record linkage as well. So what do we mean by probabilistic linkage method? So here we do not require that all the identifying matching variables match exactly bit by bit in order to conclude that the record pair belongs to the same person. So in general, even before the Feligy Center sort of formulated this more formal statistical test of probabilistic record linkage, even previously by Jarrow and others, they carried out a frequency analysis of the data values that are necessary to calculate for each variable a score. And this score basically indicates for any pair of records how likely it is that they refer to the same entity versus maybe they refer to the same person by chance. Maybe these matching variables match by chance. And obviously, if we have a matching variable, and it's quite rare, an uncommon value agreement should give you stronger evidence for a linked pair, for a linkage. And so the idea is that we're going to build these scores, and that the large scores that are assigned to the matching variables would, definitely indicate more evidence of a linkage. But the small scores will be assigned to matching variables that don't match. And the idea is that because there might be errors in these matching variables, I can't say exactly 0 chance of being a correct match because we have errors in the data. So the fact is that even a match, is not the right person, there's still a small score, a small chance that that match variable might be an error, and in fact, it is a true match. So the idea is for each matching variable, we sort of calculate these scores, and then we sum up these scores over all the matching variables. And then we, as any statistical test, we compare the sum to a threshold to determine whether the pair is a true match, a non-match, or whether we should send it off to clerical review. So how do we set these thresholds? Well, the thresholds are, again, this is classic Neyman Pearson statistical testing. The thresholds need to be set based on minimizing errors. So we have the type 1 error and the type 2 error. The type 1 error is the error of linking unmatched records. So erroneously saying this pair is a true match when in fact it's not a true match. And then the type 2 error is not linking a matched record. So I have, say 2 data sets, but I kept them separate, and the residuals, I didn't link them. And the fact is that the agency, the person carrying out the record linkage, just in statistical significance testing, where you decide on a 1% p-value or 5% alpha level or significance level, you decide on how much you're willing to be in error. Now, in fact, you don't have to be willing to be in error for both types of data. In fact, erroneously linking a matched pair when in fact they aren't really a true match is quite a serious error, versus the type 2 error where I didn't really put these pair together, particularly because in record linkage, we carry out an iterative process. So maybe under this setting, I did not link the pair, but maybe in the next iteration, I will bring these pairs together and link them. And so we have to set these error rates, 1% error, 0.5% error, sort of depending on the application. And then based on this classical Neyman Pearson decision theory, we have to determine the thresholds above which, that sum of scores will be determined a true match, below which the sum of scores are is below a threshold, it would be determined a non-match, and that in the middle, we need to send off for clerical review. So the probabilistic record linkage is more computational demanding, so we'll talk about how we can try and mitigate some of these computational issues. And it's actually pretty easy to program, and there are a lot of R packages out there now doing probabilistic record linkage. I'm sure you can find them in CRAN. But the idea is that we sort of overlook, it reduces the number of missed matches because there are inconsistencies or errors in these matching variables. And we actually account for these errors into our score, right? How likely is this particular variable to be an error? And this will allow us to, based on this chance, this probability, to determine the score for that overall matching variable. So it's a very important matching probability. So getting into these scores, giving you a little bit more introduction, a little bit more detail before I start bombarding you with some statistics. The idea here is to try and get these frequencies, or in the end, we'll talk about probabilities. And the idea is that not all matching variables give you the same amount of information, as I already hinted. So matching on gender should not give you the same weight as matching on your last name. And uncommon value agreements must give stronger evidence for linkage. So this is what I mean by needing to carry out a sort of a frequency analysis of your pairs. So to incorporate this sort of discriminating power of the matching variables, The scores for each matching variable are computed as a ratio, and they're a ratio of two frequencies. So the numerator of this frequency is the number of agreements of a particular variable in record pairs that represent the same person. So given I have some gold standard data, some test data, perhaps I have the linkage from the previous census and coverage survey, but I have some sort of test data, and we will be talking about what happens if I don't have test data and how I can estimate these scores using the EM algorithm. But assuming I've got some gold standard test data, I can look at these possible pairs and I can see, okay, I'm measuring on a gender, and really, you know, gender is pretty accurately measured. There is some measurement error, there's missing data, right, that I'm not able to link together. And so I can sort of incorporate that level of error into that numerator of the score. Now, obviously, the more errors there are, the smaller the numerator and the smaller the overall score. So you can see how that works. In the denominator of this ratio are the number of agreements in a variable in record pairs that are not the same person. Now, you can see this is a conditional probability, but in fact, because the comparison space, the number of pairs is so large, you can kind of think of it as a marginal probability. What is the chance of a random agreement in record pairs? So for gender, for example, there's two possible categories, male or female. So a random agreement can be 0.5, 50%, or month of birth, 1 out of 12. So you can think of that in terms of your, you know, number of random agreements. But theoretically, it's a number of agreements in record pairs that do not belong, they're non-matches, they do not belong to the same person. And in fact, this is a denominator. So for example, if I have you know, gender, which is a random agreement of 0.5 in the denominator versus month of birth, which is 1 out of 12, you can see that the smaller the denominator, the larger the score, right? So we want to have variables that discriminate pretty well between individuals, and that's the denominator. So more formally, there are 3 parameters for a successful probabilistic record linkage. Number 1 is the quality of the data. So that's what I was talking about, that numerator of the score, how well, you know, how well the data is represented without errors. And then the second one is the denominator, the chance that the values of a matching variable will randomly agree. So you want to have variables that discriminate well, have a lot of categories in them, like last name. And then, but there is a third probability that's very important, a third quantity, and that's the ultimate number of true matches that you might expect in your comparison space. So for example, if I'm matching the coverage survey to the census, I would expect to find, you know, really a high number of matches. If I'm trying to merge, say, the labor force survey with the income survey, I'm not going to find any matches. And there's no point, or very few matches, but there's no point in trying to conduct a record linkage. So you really should be sure that the expected number of matches, it's a prior, it's your belief, it's your prior. Your expected number of matches should be reasonable, right? It should be maybe 5, at least 5% of all possible pairs, but it should be a good number, a healthy number, so that we can, you know, estimate these things and carry out a good record linkage. So does anybody have any questions before I get into more details on the parameters? I will maybe go back to the screen, or if somebody can monitor the chat, because I don't have it. I'm on full screen. Are there any questions so far in the chat?
There are a couple of questions not in the chat, but in the Q&A.
Okay. Do you want to present them now?
Yeah, I think it's a good idea. Although the person mentioned that apparently I think you answered during the presentation, but I think it's a good idea to go back. Do the variables themselves matter? What if you have situations where there are variables that match, but they are not very granular? Like I have the same zip code and gender and age as my neighbor. So if zip code and gender and age were the only variables available, variables all matching would lead to a false positive.
That's right. I mean, so one of the things we'll talk about is that you have to add enough matching variables so that you uniquely identify an individual. Otherwise, you won't be able to determine if this is a correct match. You might get a cluster of possible matches, but you won't be able to say which one is the true match. Mm-hmm. And so in the class, again, I'm not talking about, there's in current research of entity resolution and clustering of pairs, etc. Here I am focusing on the classic 1969 Linkage Center paper where our matching variables can uniquely identify an individual. So we have enough variables to do that.
Okay, great. Thank you. That was the only question so far. So I encourage people to place questions in the Q&A, and Natalie will stop
periodically.
Okay. Yeah, exactly.
Thank you. Thank you for monitoring that Q&A board. Okay, so I mentioned there are 3 parameters to ensure a successful record linkage. So now I'll get into a bit more detail, and I'll start, instead of saying things like chance, I will give it a definition of a probability. So as I said, the numerator of that ratio of frequencies is based on data quality. And that's the degree to which the information contained for a matching variable is accurate and stable across time. So any data entry errors, missing data, false dates, this all diminishes the accuracy and produces low quality data. So we need a parameter that is able to tell us how high quality is this particular matching variable. The higher the quality of the data, right, the less errors, the more likely we would have a correct match. So the notion of data quality is reflected in that numerator of this frequency ratio. And it is called in the, Linkage Center framework, the M probability. M probability is the probability that a matching variable agrees given that the pair is the same person. So it's just, and it's defined at the variable level. Right, it's defined at the variable level, and it's just looking at these 2, cross pairs and seeing, well, how many errors do I have in these matching areas? How many missing data? How many erroneous matches? And certainly for last name, that's why I was going to talk about pre-processing for first name, last name. There could be lots of spelling errors and nicknames, etc., etc. So M probability is very important. The M probability, that numerator is measured at the variable level, right? How much error is in this matching variable? It's also referred to as the reliability. So that's the M probability. Now let's go to the denominator of that frequency ratio. That is called the U probability. As I said, it represents just the number of random agreements in the data. Put any pair together. What is the probability that the gender will be male or the month of birth will be January? So it's the probability that a matching variable will agree given that the pair is not a true match, but because we have so many pairs in our comparison space, you can think of it as sort of the marginal probability. What is the chance of a probability of a random agreement? So in that case, the U probability is approximately 1 over the number of values. It's sort of referred to as the discriminating power. And in fact, you don't need a test data and you don't need a fancy EM algorithm to get a U probability, because you can think of it just as the marginal probability, as how well this variable discriminates between persons in the data. So for example, if I'm looking at schools and I have an all-female school, there's no point in using gender, because everybody will be a female, right? So there's no discriminating power at all to that matching variable. But if you had a unique ID number like social security numbers, we would not expect a random match there. We would only be worried about quality issues and errors in the Social Security number. And in fact, as I probably hinted, if I have a very good ID number, the Social Security number, I would first do a deterministic match and then put all the rest in a probabilistic match. So the key technical issues are we have to have good quality identifiers that are able to discriminate between the persons to whom the record refers. And I am assuming that we don't have duplicates in the data. If you have duplicates, we can do a record linkage, probabilistic record linkage to first deduplicate the data. But I'm assuming that we have no duplicates and that the number of matching variables are able to uniquely identify an individual. We need to decide whether discrepancies in the identifiers are due to mistakes in the reporting for a single individual. And we have to be able to process a large volume of data within a reasonable amount of computing time. So these are the key technical issues. And so we're talking about the M probability, the U probability, and of course, in the end of the day, we have our prior, we have to make sure that we have enough matches in our exercise of linkage in order to make it worthwhile to be able to carry out a successful linkage. So I'm going to give a little bit of rundown on the pre-processing, string comparators, and blocking, and everything I'm saying now in a few slides, just multiplied by a million, because this is all the work. And in fact, there's a lot of good packages out there that do probabilistic record linkage and VM algorithms and things. But most times, these sort of pre-processing is done in-house. So if you're in your office and you're thinking about doing record linkage, a lot of this has to be done in-house for the pre-processing. So pre-processing and data cleaning are the most difficult and time-consuming steps of record linkage, but you have to do it in order to get a successful linkage. You need to think about reference numbers and if we are doing multiple passes through the pairs, using different matching variables, different what we call blocking variables, which I haven't introduced yet, but another linkage that's important here, another variable that's important. You might think about having these reference numbers that relate to your iterations of passes through the data. That's just a technical thing, but the most important is to make sure that you a priori treat sort of missing, miscoded data. Obviously, you're putting pairs together. So if it's missing with a minus sign in one file and missing with a 9 in another file, that's not going to help you, right? You have to make sure that everything is has the same definitions, the character strings, first name, last name, everything has to be the exact number of characters in the string. If you have first names that are put together, say with last names or house number and street number, you need to separate them because you're going to get a lot more power in your statistical testing of the linkages if you separate these matching variables into separate variables instead of saying 2170 Randolph, 2170, the house number is separate, the street name is separate, right? That gives you more power. So you need to be able to parse these fields into separate fields. Certainly, if you're looking at names, they have variation in spelling and nicknames and abbreviations, and there are dictionaries that will help you with differences in spelling or different nicknames like Bill and William. In that sense, you sort of have this deterministic matching to these dictionaries, and then you're looking probabilistically if any one name is appropriate compared to the other data set. So again, increases the complexity, but you need to think about dictionaries, especially for these large linkages. I don't know if there's any dictionaries that are publicly available. There might be. I know the Census Bureau has great dictionaries, but whether they're publicly available, I don't know. So the matching variables and blocking variables, I haven't defined the blocking variables yet, but those are very important. Blocking variables are variables that we use to reduce the comparison space for the possible pairs. So within a block, we only compare those pairs that match on a certain variable, blocking variable. But I'll get to that in a minute. but both files have to have the same standard formats and the same field length and coding status and the way the dates are defined, and all of these things. It's really hard to get these two files to actually talk to each other, so that's the challenge. Now, in probabilistic record linkage, we do assume that we don't have a high quality identifier, and that we basically need to put together partial identifiers, things like last name, date of birth, postcode, and we can concatenate. It's a function in our statistical packages that brings these together to produce some sort of ID number in one long string. So for exact matching, these compounded keys need to be as complete as possible, because in exact matching, we have to match exactly bit by bit. But we need to think of these matching variables in our probabilistic linkage, and we want to make sure that the matching variables define uniquely and individual, and that we don't have duplicates in the data. So things like proper names rarely change during the lifetime of a person. Natalie is Natalie, whether I get married or not. First names, initials, your personal characteristics that are fixed at birth rarely change. Your gender, ethnicity, your date of birth, place of birth, those would all be good matching variables. Your social demographic variables do change over time. So if you are using things like your marital status or street address or postcode, you need to think about the timeliness of these two data. Certainly for the big coverage surveys and against the census, those are all done more or less at the same time, so that we can use these demographic variables as good matching variables. A little bit about phonetic codes. I mentioned this in the scenario of fuzzy matching. Phonetic code basically copes with spelling errors. So it's a phonetic code which gives you like a numerical number to replace the spelling, so that names that sound the same get the same code. So, for example, you have SoundX. I mentioned SoundX because it's in all the statistical packages, but there are a lot of better phonetic codes out there. So SoundX code, for example, read with an I or read with an E is R300, right? So you can use a fuzzy matching or use the SoundX code to introduce more errors in deal with spelling errors. And there are also variations for cultural names. Some names focus a lot on vowels more than other cultural names. So it's a bit challenging on other cultures' names, but there are, packages out there. So, and I mentioned that because the fuzzy matching will sort of try and match on the SoundX code. The truth is, though, especially with people, the SoundX code is very rarely used, and what is used is typically the Jarrow-Winkler string comparator. It was developed first by Jarrow, but it was adapted by Bill Winkler to make it a bit more powerful. You put weights, depending on where the errors were. But basically, the string comparator is a number between 0 and 1, with 1 denoting a perfect agreement and a 0 an imperfect agreement. And just if you want to have a little fun, I gave you the formula. You can go away and do this on your own. But I gave you the formula. It's because there's 3 terms in it. It has to do with the string lengths, the number of common characters in the strings, and also the number of transpositions. Remember, there was a time when people used to key in the data, and not these web forms that nowadays we all key in our own data. But it was very possible to interchange letters, like as you can see with Billy and Blilly on the bottom. That was a very common error, and one that they wanted to focus on certainly at the Census Bureau. And anyways, so this is a string comparator where there are 3 components: the number of common, and common has to be sort of within the first half of the word. So the number of common letters divided by the first string length, plus the number of common letters divided by the second string length, and then you have this 1 minus a half times this half transposition. So Blilly and Billy, that's 2 transpositions because the I and the L are interchanged. And then you can see, and then it's a weighted average, so we multiply by 1/3. And so here you have two examples of string comparators, 0.933, 0.933 for different adaptions of errors in Billy and Bill and Billy and Lily. So it's kind of fun to play with. And I will be showing you in the end how we can incorporate these types of string comparators into our linkages. So of course, string comparators are very widely used, especially when we're trying to link people. And I also want to mention bigrams or trigrams because I'm going to give you a slide also on probabilistic record linkage. So a bigram is another string comparator. There are things like Jaccard scores and all sorts of computer science similarity scores as well. But what the bigram does is it takes a word and splits it up into, sort of the bigram will split it up in 2 bits. So B-I-I-G, G-R-R-A-A-M, those are the bigrams for the word bigram. And then the string comparator is basically taking the proportion of common strings divided by the average number of substrings in your 2 pairs. So it's a type of a Jaccard score, basically. And these types of comparators are used to, especially when we have anonymized strings, to avoid frequency attacks. So I'm going to give you one slide on privacy preserving record linkage, where there's a lot of people working on that, because not everybody has access to names and addresses, but there is a way to anonymize those strings using hash functions. And then we could use things like similarity scores to carry out a linkage for unanonymized data. Now here I'm going to define what I mean by blocking variable. The number of possible comparisons increase when the product of the file sizes is large. So if I have 2 files, both of size 10,000, you can imagine when I bring all possible pairs together, I'm going to have 100 million pairs to compare. So the computationally is just enormous. And so what we do is we only restrict the comparisons to blocks of data where we're fairly sure that within that block of data, they'll be the same individuals. So for example, I might block on, postcode or zip code. In the US, it would be zip code. And the idea is that if I first do a deterministic match on all the people in file A, their zip code, and file B and zip code, and then only put those pairs together in the same zip code, you can imagine how much I can reduce this comparison space. But that blocking variable better not be an error, because if it's an error, I'll never put these 2 people together. Which is another reason why we usually do iterations and try different blocking variables and different matching variables just in case we have errors on the blocking variable. And so the idea in record linkage is to block sequentially in an iterative process, not just once. We usually do multiple passes through the data, trying to use different blocking variables and matching variables. So for example, we might block on the postcode and the initial of the first name, and then we carry out our linkage, we get a final set of matches after the clerical review, and then we still have our residual files that we haven't put together. So now let's try and block on a completely different variable like year of birth. Okay, so you can see how that works. And let's try and bring more residuals together, more pairs together, and then keep working through the data until eventually you don't have, hopefully if you a good process, you end up with a very few records that you can actually don't need to do any more blocking. I would just try all possible pairs. And so that's the idea in record linkage. So I'm going to pause here for questions and all of the pre-processing. As I said, I barely touched on a few of these topics, where this is really 99% of the work. And then I'm going to get into here now some statistics and talk about the Felagi-Sunter theorem and probabilistic record linkage. So I'm going to be introducing it more formally in the next section. Are there any questions on this introduction?
Yes, there's a couple of questions which I'll read to you. So the first one is, what happens if there's a duplicate in one of the files? Like if someone moved and they're in a table with both addresses.
Okay, so Presumably, if they're duplicate, presumably we want to get rid of duplicates. But in this case, you're saying actually it's not a duplicate; they just appear in different addresses. So hopefully you have a more updated, data set in file B, say, and you would select the right person in the right address. Nowadays, agencies are moving to sort of administrative data censuses and stuff. And there's a lot of effort to try a priori to identify the right address using signs of life and things like that. But yeah, you might end up with a cluster of possible pairs that you might need to take to clerical review in that case.
Right. So the second question is, in practice, are there processes, are these processes programmed by the person who tried to link records, or are there pre-existing software one can use?
So that's a good question. I don't know if there's pre-existing software. I know there's a new paper out with Rebecca Sturtz talking about pipeline, cleaning in the pipeline, and that might be helpful. I'm not aware of any, packages that does data cleaning because it's so dependent on what files you're trying to merge. I know that many agencies really struggle because they have to build these pre-processing in-house. There's certainly packages out there that do phonetic codes and string comparators and all of that, but just to get these two files to talk to each other with the same string lengths, the same definitions, I think that's something that has to be done by the linker or by the agency doing the linkage. I don't think you can get around looking for a package that does that.
Great. So those are all the questions for the moment.
Okay, so I was going to be paused a bit because now we're going to do some statistics. And I'm going to use the notation in the Linkage Center paper. So when you finish this little lecture and you want to actually read the paper, hopefully these notations will be useful for you. So I'm using the same notation as the Linkage Center paper. So we have two data sets in the Linkage Center framework, and he calls them A and B, and they have NA records in file A and NB records in file B. So little a belongs to capital A, the data set A, and little b is a record that belongs to data set B. And the idea is we're going to put together all possible pairs of A and B. So we have a set now of matching variables A, B, where A comes from the data set capital A and the record B comes from the data set B. Now we're not looking at all variables, we're looking at K matching variables. So we're going to denote those by X as our vector of matching variables. So we've got X of A on data set capital A, and we have X of B, and these are the K matching variables for the entities A and B on these two data sets. And again, we're going to assume there's no duplication, so we can get a good linkage. And the idea is to find a set of matches M, where A is equal to B, and a set of non-matches where A is not equal to B. So this is our aim. This is set theory, right? We're going to try and put all these possible pairs into two sets, the M set and the NM set. Ultimately, we're going to also have a clerical review set. So in order to do this, we're going to define a comparison vector for each record pair. And this produces a comparison space, C. So this comparison vector, little gamma, belongs to a set of all possible comparison vectors, and we denote that by capital gamma. And in sort of the Linkage Center paper, we're going to keep it simple. We're going to denote this comparison vector as just a 1-0 indicator, telling us, is this an exact agreement 1, or if it's not an exact agreement 0. So I'm not accounting for possible string comparators or anything. It's just, it matches, it represents, it's equal on the first matching variable. It's not equal in the second matching variable, and it's equal on the third matching variable, assuming you've got 3 matching variables. And in fact, Felage Hunter used 3 matching variables, which I'll explain why they show their example on 3 matching variables. So think of this sort of first name, age, last name. And so if we have 3 matching variables, right, and each matching variable can be 1 or 0, whether they agree 1, disagree 0, how many possible comparison vectors are there in my gamma space? In that case, it'll be 8. So 1, 1, 1, 1, 1, 0, 1, 0, 1, you can do the combinations. So in this case, one example is 1, 0, 1. It could be 1, 0, 0, 0, 1, 1. So the idea is that for each one of these comparison vectors now, we're going to define our M probability, a U probability, and the prior, what is the expected number of correct matches. So formally, that M probability that I've said in words is what is the probability of agreement, or 101 or 111, given it's the same person, right? So given it's a match. Again, this is where we're going to need the EM algorithm or test data to try and get those values. The U probability is the same thing. Looking at the probability of that, obtaining that agreement vector, 101, 111, given it's not a match. That's the U probability. Okay, and then we have the prior, the probability of a match. So what we do is, of course, we're interested in the probability of a match, given that I've observed this agreement, 101. So we're not interested in the M and the U. We need to turn things around. And how do we turn things around? How do we get the probability of a match, given I've observed a particular agreement vector? We use the Bayes theorem. So I wrote here the Bayes theorem for you, and I wrote out the denominator of the Bayes theorem, and I also put it in the formulation of an odds. So ultimately you have 1 over 1 plus this ratio. Remember, we're going to get back to this ratio that I defined in words, but now we're going to talk about it in probabilities. So it's that ratio that we're going to be using as our score. Okay, so you have as the ratio, the U probability times 1 minus the prior over the M probability times the prior. Okay, that's this likelihood ratio. So the test statistic, again, in order to maximize this figure, this odds, is we need to maximize what we call the likelihood ratio. So the likelihood ratio is the M probability over the U probability, and that's what we're going to use as the score, the likelihood ratio. Again, classic Neyman Pearson testing that we did all in our undergraduate statistics courses. So now we have this score, this likelihood ratio. What we're going to do then is for each agreement vector, we're going to sort all of our possible pairs from top to bottom, and the high likelihood ratios will be the likely matches, and the low likelihood ratios will be the non-matches, and somewhere in the middle, we're going to have to do a clerical review. So the whole notion of how do we determine these thresholds, that's going to come from our error rates. So that'll come in a minute. So in the Felage Hunter framework, we have a linkage rule where we want to take our all possible comparison vectors and move them into 3 sets: the match set if they're above W plus, the non-matches if they're below the threshold of a W minus, and in the middle, we're going to take them off to clerical review. So you were asking, well, how do we get from this likelihood ratio and these vectors into what I've been talking about previously, where I was doing not as a vector, rather I was doing separately, matching variables separately, like age, sex. So in the Felage Hunter original framework, there is a very, very strong assumption of conditional independence. In other words, the fact that we have an error in last name is completely independent to the fact that we have an error in first name. Okay, so these error structures are independent. Now that's quite a strong assumption, especially in the old days when we used to use paper for our forms or questionnaires, and the fact, and they would have sort of optical readers. So the fact that they were missing an R in one, it didn't matter if it was first name or last name. So it's quite a strong assumption, and there has been a lot of work to try and reduce this assumption. But nevertheless, I'm going to stick with this assumption of conditional independence, which means that that comparison vector where it had 1, 0, 1, given it's a match, the M probability, I can actually break that up into their marginal probabilities, right? That's the definition of independence. That the probability of an agreement on the first matching variable given M times the probability of an agreement on the second matching variable given it's a match times. And I can turn those into separate probabilities based on the assumption of conditional independence. So now I'm working with separately, each matching variable separately. And then you're asking yourself, well, you talked about sums and not multiplication. So for that, as we do for any likelihood, we take the log, which makes things easier. So taking the fact that we're maximizing probability or maximizing the log of the probability, it doesn't matter. And so we have now the score function, which is the log of the M over U for the first matching variable plus the log of the M over U for the second matching variable plus the log of M over U for the final matching variable. So it's really simple, right? And so the idea is that for each matching variable, we need to, think of what the probability of agreement given it's a match, what is the probability of agreement given it's not a match. We have the M probability, we have the U probability for each variable, and we can develop a score. Really, it's quite easy, and we'll have a little example. But what was really nice about Linkage, and for this reason, they used 3 matching variables. Now we can decompose the probability of agreement for a record pair, right? This is a law of conditional probabilities, really simple. Now on the left-hand side, we obtain the proportion of the patterns in the population, which is known, right? We know the left-hand side, and we actually can decompose then this formula to get these MU probabilities, U probabilities, and the prior. So assuming a simple agreement-disagreement pattern, we have a sort of Bernoulli frequency distributions giving these marginal M probabilities and U probabilities. And let me just say, so in this framework of Linkage, they actually solved this problem by pen and paper because they had 3 matching variables. So that gave us 6 unknowns, the M probability, the U probability for matching variable 1, M probability, U probability, matching variable 2, M probability, U probability, matching variable 3, and the prior. So there were 7 unknowns. And each agreement, there were 7 equations because 1, 0, 1, 1, 1, 1, 1, we can observe those patterns. In any case, my point is that Linkage with these 3 unknown probabilities for each matching variable and the prior were able to calculate without any test data what is the expected M probability, U probability simply by decomposing that equation into the law of conditional probabilities. Now, at the end of the day, we usually have more matching variables than 3, so there are there's optimal solutions. And we actually will be using, and I'll show you how we use the EM algorithm to get to estimate M probabilities, U probabilities, but we don't necessarily need training data, which is nice. So the U probabilities, as I said, we really don't need training data. We can actually use random agreements. And in fact, a lot of applications you'll see, not only do they do random agreements in general for month of birth, they will also use random agreements based on the category. So for example, my last name is Shlomo. Would that carry the same weight if somebody's last name was Smith? Right? So you can actually, at the level of the U probability, just go through all the pairs and say, well, how many random agreements are there on Smith how many random agreements on Shlomo, how many random agreements on Franco, right? And that you can use as your U probabilities. However, for the M probabilities, we need training data. We need matched data to see what is the level of error in these particular variables to determine the M probabilities. And so training data is great. And then I will also introduce how Feliky and Center calculated these probabilities using a form or easy form of EM algorithm, and how we do this in our applications where we have more than 3 matching variables. So just to summarize, we've got a log ratio of these M over U's given the match status of a comparison outcome. Now we can strengthen these scores by introducing these string comparators. So you can see I have a yes, no, but maybe they're similar. Maybe I've got a string comparator of 0.988. And there are ways of how we can incorporate these string comparators to sort of downweight a little bit our agreement our M over U, our likelihood ratios. So we take into account these string comparators or phonetic codes by doing some sort of extrapolation, but somehow accounting for that, even if we do this sort of EM10 agreement patterns. And the idea is that we can use these frequencies from the data, even without the need of a training data set to calculate scores from the data. So we'll just do a little quick example. I don't know how much more time we have, but we're running out of time, so I need to quick. So as I said, this is the formula for the ratio. Let's say I'm comparing now Samantha Smith and Sam Smith at these addresses. So you can see I've got a disagree on the first name is a 0. I agree on the last name is a 1. Agree on the house name, house number 111. I disagree on the year of birth, and I disagree on gender. So that's my vector 0, 1, 1, 1, 0, 0. In red, you see I'm sort of assuming M probabilities and U probabilities. Now M probabilities pretty much have to be high, right? If you've got M probabilities that are below 0.8, you probably won't have quite a successful record linkage. And then the U probability should be really small. I'll just put in something arbitrary. But look how easy it is. Once I've got the M probability and U probability, I simply take the log. In this case, I took the natural log. You can take any log. In fact, sometimes people take the log to the base 2 because it sort of gives you more minus and pluses. And yes, so if I have a disagreement, I do 1 minus M over 1 minus U. If I have an agreement, it's M over U. Another agreement, M over U, depending on the M and the U. Agreement, M over U. Here I've got a disagreement on, what was it? Birth date, year of birth, 1 minus 0.9, 1 minus 0.1. So it's 1 minus M divided by 1 minus U. And anyways, I end up with a score of minus 8.81. So I do that for all of the pairs in my data set. Okay, any questions? Quick questions. We don't have that much time.
I'm not seeing any questions in the chat. Someone does have their hand raised. I would ask if you have a question to please put it in the chat, because that's how we're doing.
Maybe in the end we can have time to let people in as panelists if they want to ask verbally, or you can also try and just, schedule a meeting with me or email me directly if you have more detailed questions. Okay,
No, I'm just saying, let's just continue.
Okay, yes, so continue. So I wanted to introduce the EM algorithm. We don't have a lot of time. So as I said, the EM algorithm, we have this lambda K for an indicator variable, typically 1, 0, following the Bernoulli distribution for a particular pair. So the simplest case is 1, 0. So then they're really easy to do the EM algorithm. In this case, and as I'll show you, you can also introduce the string comparators to try and introduce a bit of fuzziness into these strict 1, 0 agreement patterns. So we have this agreement vector, this gamma J, but what we don't know is the matching status. We don't know the M probability, we don't know the U probability, or the matching status representing the same person, or the match status if it doesn't represent the same person, the set of NMs. And then we also have a prior. So these need to be estimated in our EM algorithm. So again, same formula that I showed you before, applying the Bayes theorem for the simple case of the 1-0 agreement and using the Bernoulli distributions. This is what the updated estimate is for the match probability given it's a match, and the match probability given it's not a match. And basically these are just multiplications of M's and U and M's and U's. So as we saw, we did we took the logs, so we have log of M plus log M over U, etc. And basically it just says these are ones and zeros. So if it agrees, it's an M. If it disagrees, it's a 1 minus M, right? So that's all they are in the numerator and denominator. So that's the E step, really easy to program it as well. And then the N step tries to update the conditional probability of obtaining the observed agreement for the case variable, giving the record pair as a match. That's the M probability. So here's an estimate of the M probability and the update for the U probability and an update of the prior. And then it just iterates back and forth. Now it introduces these MKs as, as in the next version of the E step, right? And we get an M step, and it's so simple. But the idea, again, this is a very, the notion, basically just decomposing that probability of observed, observed agreement patterns, right? That's all we're doing, we're decomposing it. As I said, if we had 3 variables, we could do it pen and paper, but because we probably have more variables, we need to optimize it. And therefore we use the EM algorithm. And this is how we can adjust for the string comparator. So given I've got an M and a U probability for agree, disagree, basically we can sort of get an assigned weight by down weighting a little bit the agreement score, looking at the extrapolation of the difference between the agreement and disagreement score, and then introducing that 1 minus the string comparator. So it's a way of introducing more fuzziness into our strict, likelihood ratios with 1-0 agreement patterns, and allowing for a little bit of fuzziness to put in agreement patterns. We saw in the previous example, we had Sam and Samantha. We had birth year that was only different by 1 year. We don't want to perhaps say that that's a complete disagreement, right? So we can introduce, string comparators. Well, how likely are they actually that they might be the same person? The same with missing data. Any type of string comparator. For numerical values, we often use a string comparator for birth year, like using the exponential functions, so that the farther apart they are, the larger they are. But a difference of 1 is going to give you a very, very large similarity score. So there are ways in introducing fuzziness into the strict EM algorithm and assuming Bernoulli distributions. So finally, and we probably have a little bit of time, this is the process. I won't go over it more, but basically it's to select your matching variables, your editing, the parsing, phonetic code, standardizing, blocking. First, do a deterministic method. You might be lucky and find matches, put those aside. Then start with your probabilistic method, calculate your probabilities, agreement ratios. Again, we're going to talk now about setting the thresholds, matching the variables, doing the clerical review, going back perhaps to another pass in the data using different blocking variables. So on the thresholds, a few words here. Now, we don't have normally distributed data, but it's very convenient. The scores are not normally distributed. They're actually, we can turn them, of course, into logistic scores, but it's convenient to see it as a mixture of normal distributions. And if we take a look at what we have here, we've got 2 sets, right? The matches and the non-matches. The matches would have the higher scores on the right-hand side, and the non-matches, which there's a lot of, so we've got a high mode there, would be on the left-hand side. So assuming that the x-axis are the ranges of these scores. And you can see that what we want to do now is to set a threshold here, where we would automatically say these are all matches. We would set a threshold W minus, where everything on the left are the non-matches, but you can see now, and I'm going to drill in the next slide, that we have a mixture. okay? What do we do between the W minus and the W plus? So now I'm focusing in on that area. And you can see that, we're going to get some false positives. We're going to get some false negatives. However, we set these thresholds. And the idea is that we want to keep these at a minimum. And in fact, you can decide, especially if you have test data, how much you're willing to be in error. So these empirical distributions can be used to determine the thresholds. Typically, you can just try eyeballing, just sorting the links from top to bottom. These all look like matches. These don't look like matches. And then taking that off to clerical review. Now, the true Linkage theorem says that if you prescribe your error rates, the type 1, type 2 errors, the clerical review will be optimal. Okay, so there's a theorem in the Linkage saying that the optimal set for clerical review, given your predefined error rates on the type 1, type 2 error, will be minimal or optimal. But at the end of the day, people who are doing the link agencies that are doing these linkages are also a huge function of their budget, right? So we can't ignore how much budget is involved when we have to clerically review possible pairs. So again, this is just reiterating, we have the false positives coming from the non-matches. We have the the non-matches pairs, the false negatives. And again, we might want to be more concerned with that area A, given that we're not going to be looking at them again because we might be falsely linking people when they're not supposed to be linked, right? So they might want to have a tiny error there. Whereas in the false negatives, we might be doing more iterations in the data, so we can allow for a little bit more error. Now, to look at our classic Neyman Pearson, we have a matrix, a dispersion matrix, where our null hypothesis is not a match, our alternative hypothesis is a match, and then we have our score, our likelihood score, and we need to decide, do we reject or not reject the null hypotheses based on our test score, which is the likelihood ratio. So the type 1 error, we reject the null hypothesis when the null is true, or we declare that a link is indeed a pair when it is not a match, which is a problem. And the type 2 error, where we don't declare a match when indeed it should have been a match. And maybe that's not so bad because we'll be recircling through the data. But these are typical scores that we need to look at, and classic row curve stuff, the false negative rate, false positive rate, also known as the specificity and the sensitivity or recall. But in record linkage, we definitely look at something called the precision, which is the number of true positives over the true positives plus the false positives. So it's basically looking at that row to see how successful we were in linking the pairs out of the total number of pairs. So in record linkage literature, you'll see a lot about the precision and a lot about the recall, and also combinations of these two goodness of fit criteria. Okay, we've got 10 more minutes maybe, so I can go over a bit quickly some of this, the rest of the slides, just to give you a flavor of some new extensions. Are there any questions now that I finished the sort of Linkage component of record linkage?
I'm not seeing any questions in the Q&A. So if people have questions, please put them and we'll answer at the end, okay?
Okay, so I will stop now at the end. I'll try and finish in 10 minutes or so. So I can talk about 1969 Linkage framework without mentioning all of the brilliant work that's been going on in the last decade or so. And I'm just going to give you references, right? I don't have time to get into it. Of course, in order to read this literature, you'd have to have a good background of the Linkage probabilistic record linkage. So I'm happy I devoted most of my time on that. I'm giving you lots of references here for newer works, certainly in the Bayesian frameworks, including the hierarchical and empirical Bayes, where Fortini, for example, in 2001 put in did a one-to-one match. I didn't talk about one-to-one or one-to-many. I think somebody asked about a one-to-many linkages previously. But it was a one-to-one match, and trying to put Dirichlet priors on these distributions, certainly a good way to go. Stanley did some work also on Bayesian frameworks, but the most important being able to quantify the uncertainty about the linkage, because at the end of the day, an analysis needs to know the error rates, which will be my last slide. And certainly the brilliant work of Rebecca Sturz talking about entity resolution and deduplication as a clustering problem. So here we, develop clustering and trying to deduplicate or find the correct links in the data in clusters of pairs. Again, using a hierarchical Bayesian approach, using Dirichlet priors and all sorts of complexities there. There's also been some work using supervised learning applications. Now that's a bit tricky using training data, because if you think of all possible pairs, how many potential matches there are very few. So you really need to have a very large amount of training data to try and do supervised learning. But then again, if you do supervised learning, you can think of all these nice machine learning techniques, right, that we can use for classification, random forests and decision trees and all that sort of thing. So that, of course, relies on really good training data. And I found a really good article that you can read all about these extensions in Binet and Stutz in 2022. It's actually a magazine article, and so I really recommend you read it. One slide on hashing. A big area of work is privacy preserving record linkage here. We do not allow, this is if you as researchers want to do the linkage and you're not allowed to see names and addresses, you might be able to convince the survey agencies to give you cryptographic data. So we use a hash function to anonymize records. And so all of the linkages are based on similarity scores like the Jacquard score, the DICE score. You can see, for example, using a bigram of John and John, and using similarity scores, we can get a pretty good guess that that's a fairly good representation of the same person, just by looking at the number of agreements divided by the total number of bits. That's the DICE coefficient. And so it's a large amount of literature in privacy preserving record linkage. Don't have time for that. So what I did want to do is to give you a nice reference here of an overview from Schnell, 2021, that he wrote for the UK data, a UK statistical authority. So really nice overview of methods and ways to hash functions. Again, even if we're hashing, we might have frequency attacks like Smith. You might be able to identify Smith, even they're hashed because it's such a common name in the United Kingdom, for example. So, there are ways to get around that, other ways of anonymizing, bin-wise hashing, and all sorts of complexities there. And finally, just to say a bit of words about analysis. At the end of the day, you have linked data. You want to be able to analyze the data. Sometimes you're just interested in a total, like the total number of traffic accidents that ended up in mortality. So maybe the false links will cancel out the true links, and maybe it's not so bad that you might have linkage errors. But if you wanted to do any sort of longitudinal analysis or comparison of persons, you better make sure you have very low errors in your record pairs. So it kind of depends on the purpose of the linkage. But just to say, to analyze data that has linkage error, we have to think about that we have a correct link, y star is equal to the true y, with a probability q. Hopefully q is 99.9%. But we might have errors where, I should have had y star not equal to yj, apologies, with a probability of 1 minus q ij should be. Anyways, but the idea is that I have an error matrix, okay? So once we have an error matrix being a correct link or not, or not being a correct link. The idea is to use our standard measurement error literature to account for errors in the record linkage. The problem is that QIJs are not known. So conceptually, you can think of linkages as actually a representation using a permutation matrix. So if we sort of use vector algebra, we can look at our linkages as a configuration matrix times our X variable in file A and our Y variable in file B that is putting together these records. X3 goes to Y1, X1 goes to Y2, X2 goes to Y3. So if we're naively looking at a count, X transpose Y star, we're actually looking at an X transpose CY. So if we put on a distribution on this random permutation matrix C, and we can define a distribution around that, and that Q is now the expectation of C given the X variables and these record linkage parameters that are denoted by psi. We can then correct any analysis. For example, for a contingency table, we can correct our analysis by X transpose QY, okay, Y star. So we can introduce Q into our contingency table literature or regression models in order to alleviate any record linkage errors. Now, we don't know Qs. What we might know on this error matrix is some sort of overall error rates. In that case, we might have one overall error rate because that's all the data, collection agency told us. There's 99% error free and 1% error rates. And so we can sort of develop our own error matrix, but it's very much kind of like errors in completely at random sort of thing. You can put on the diagonal 99% and the other 1%, the error rates that record 1 went to record 2, record 1 went to record 3, etc. But anyways, you can produce this sort of error matrix Q using this notion of errors completely at random, or if in blocks, you can do a block diagonal error matrix. So I know I'm going really fast, but the point is you can look in the literatures that I have here. Chambers 2023 gives a good overview of thinking about how we can get an error matrix Q in order to correct our contingency tables. Here I'm showing you how we can correct our regression coefficients. You've got the Lahiri-Larson estimate, which again introduces the Q, and a more efficient estimator is the blue, of course, where we introduce the variance of the distribution based on this configuration matrix, the sigma. And Chambers also talks a lot about how he estimates the sigma to get the blue estimate for the beta coefficient in a regression model. And there's also another paper, which I'm citing here, which actually says, what, if you have missing at random, we can probably correct for the, the links we're not sure about and just do multiple imputation. So there you go. There's another approach. So this is a list of all the references I cited, and I'm happy to take questions now in the last 5 minutes, but I'm more than happy. You have my email on the first slide. More than happy if you want to meet with me or talk to me or ask me further questions, and I'm happy to answer your questions. Shall I stop share then?
Okay, yes, thank you so much, Natalie. That was really interesting and really clear. That was fantastic. So not seeing anything in the Q&A, so if you have a question, this is the last chance. And in the meantime, I'm gonna make some announcements. And then Chase from Statistics Without Borders will also make an announcement. So I'm gonna, and Alex, you have an announcement too?
No, I have a quick question. Because I'm completely new to this area of record linkage, I find it quite challenging, to be honest. And one of the things that I keep thinking about is variable selection, like how to choose the variables that you are going to do the matching.
Well, I mentioned the first time they have to be unique, little errors, timely, what else? Can't remember what I said, but they have to be able to identify, when you put them together and, concatenate them together, they have to be able to uniquely identify an individual. And the ones, the matching variables like last name, the ones that have very high discriminating power, they're going to give you the highest scores because that's in the denominator. And again, you can even do character specific. You can even give different scores if it's Smith or Frankel.
So it's really through conversation, right? Performing some statistical variable selection method probably doesn't help much.
No, that wouldn't help. It's not a modeling. It's not a modeling exercise.
It's really,
Yeah, and I think most of your participants are going to say, well, I can't uniquely identify anybody because all I have is age, sex, postcode. And but I did want to mention that hashing, because what we need to do is to be able to convince our agencies or the data archives to give the data with the anonymized codes, because we can still do a lot with that. And there's no reason why a data archive is giving the data set can't give us last name but not anonymized, or backgrounds of anonymized strings. That helps.
Yeah, thanks a lot. I really enjoyed it. Thanks a lot.
Yes, thank you so much. I enjoyed it as well. So quick announcements before we run out of time. So let me share my screen really quick. Okay, screen 3. Are you seeing the webinar announcement? Okay, so our next webinar will also be very, very interesting. It's an overview of statistical data integration in health policy, and it will be on July 24th at 12 p.m. Eastern. Again, it's 90 minutes, like all our webinars. And it's held by Dr. Susan Paddock, who is Chief Scientist and Executive Vice President at NORC at the University of Chicago. And I think it will be extremely interesting. She's going to talk about various ways of combining information and various methods to do so. In fact, one of the methods he'll mention is record linkage. So now you'll know about that. She'll probably refer back to this one for that. But so this will be extremely interesting. So we encourage you to attend, and the information is already in our website. Maybe we should share the link to the website here.
I shared it, Carolina. I just shared it.
Wonderful, thank you. So we encourage you to attend. We think it will be also really interesting. And the other one I want to share, this is a really exciting tool for those of you who are doing some work with survey data. So the Journal of Survey Statistics and Methodology has a special issue coming up on survey research from Asia, Pacific, Africa, the Middle East, Latin America, and the Caribbean. And the guest editors are from different places of the world. I'm one of them. We have Mamadou Diallo, Sangi Lee, Sharon Sharma, and Denise Brito Nascimento Silva. So we encourage you to submit if you have a paper that you think would be great for this issue. Basically, the topics can be pretty much anything that is normally covered by this journal, which is survey statistics, survey methodology, and applications, but with applications from other countries, from the countries mentioned here, the regions and countries mentioned here. So I think it will be an extremely interesting issue. So submissions are due by August 16th. This whole announcement is now on our website as well. So I don't know if, let's see, we share it. Yes, so Donna kindly shared the website. And the last reminder I wanted to do is, in the last couple of years, ASA lowered the membership fee for developing countries to $10 in an effort to encourage more people from around the world to become part of ASA. I think ASA for me has been an extremely rewarding experience. So I encourage you to check out the membership page at ASA, which I'll share in a little bit. Donna has shared it already. Thank you, Donna. And now I think Chase, who is our partners, he's part of Statistics Without Borders, which are our partners in this webinar series. So I think Chase will say a couple of words about Statistics Without Borders. So I'll stop sharing.
Thanks. And so just to give a quick description for everybody of Statistics Without Borders. So Statistics Without Borders is the outreach arm, or is an outreach arm of the American Statistical Association. You don't have to be a member of the American Statistical Association to join, but we provide pro bono statistical and data science services, working to improve human welfare by providing empirical knowledge using proper applications of statistical principles. So just an example of some of the projects we've worked on in the past, we've evaluated the effect of ecology conservation for chimpanzees in Sierra Leone. We've used surveys to determine the magnitude of the earthquakes in Haiti in 2010. We have been associated with water conservation for assisting with projections on water conservation for a number of countries. So if any of those things sound interesting to you, I would encourage you to reach out to us, volunteer with us. The easiest way to learn more about us and to connect with us would either be through our website, which you can find just by Googling Statistics Without Borders, or we also have a LinkedIn page that I would encourage everybody to take a look at. And we've got a short video describing what we do more in detail as the very first page on that LinkedIn page. So thank you all for your time, and I hope everybody has a great day.
Thank you so much. And thank you again, Natalie. Thank you, Alex. Thank you, Donna. It was great seeing everyone, and we'll see you at the next one.
See you. Thank you so much. Thanks a lot. Bye-bye, everyone. Take care.
Bye-bye.